For decades, one question kept resurfacing in the world of transportation engineering. Where should a bus engine actually be placed? At first glance, the answer seems obvious. Why not mount it at the front, right beside the driver, just as most trucks do? It sounds practical, familiar, and easy to maintain. Yet, over time, nearly every manufacturer of city and intercity buses abandoned that layout. The reason wasn't simply to reduce cabin noise or make repairs more convenient. The real explanation was far more complex. So why did engineers eventually move one of the heaviest components of the entire vehicle all the way to the back of the bus? And what unexpected disasters plagued every design that tried a different approach?
Imagine trying to make a graceful ballerina dance while a massive spinning steel bar is locked inside her body instead of a flexible spine. That bizarre image comes surprisingly close to describing the earliest passenger buses. These vehicles inherited their design directly from trucks, and with that inheritance came a serious engineering headache. The biggest challenge was transmitting power from an engine mounted under the front hood to the rear wheels that actually drove the vehicle. To do that, engineers had to run a long driveshaft beneath the passenger floor, a massive steel tube spinning at several thousand revolutions per minute. As long as the shaft remained short, the system worked reasonably well. But once its length exceeded 3 or 4 meters, the laws of physics began to fight back.
At those speeds, even the tiniest imbalance generated enormous centrifugal forces. A barely noticeable manufacturing defect could transform the driveshaft into a giant rotating whip. Under resonance, it would flex violently, threatening to tear the vehicle's frame apart. To prevent catastrophic failure, engineers split the shaft into multiple shorter sections, connected by support bearings and universal joints mounted directly to the chassis. The solution kept the bus from destroying itself, but it introduced a whole new set of problems. Every additional joint became another pathway for vibration and high-frequency noise to travel straight into the passenger cabin. Instead of a quiet ride, travelers felt constant buzzing beneath their feet. The cabin floor also had to be raised much higher off the ground, simply to hide the bulky transmission components underneath. That meant passengers had to climb several steep steps just to board the bus, making access inconvenient for everyone.
One early example of these problems appeared in 1933 with the first Soviet hooded buses built on the GAZ-03 platform. Their bodies used wooden frames covered with thin sheets of steel. Continuous vibrations from the long driveshaft shook the entire structure so intensely that bolts loosened and wooden joints weakened after only a few months of regular service. Passengers often joked that riding one of these buses on rough roads felt less like transportation and more like sitting inside an enormous concrete mixer. The shaking became unbearable, and steep hills created an even greater threat. Under heavy load, the twisting stress on the long driveshaft sometimes exceeded its limits. When that happened, the shaft snapped with a terrifying metallic scream, instantly leaving the bus stranded. Engineers quickly realized the obvious conclusion: the long driveshaft had to disappear. Their first idea sounded simple enough. Instead of sending power all the way to the rear axle, why not drive the front wheels instead? Eliminating the long shaft would solve the vibration problem in one stroke. On paper, it looked brilliant. Reality had other plans. One early example of these problems appeared in 1933 with the first Soviet hooded buses built on the GAZ-03 platform. Their bodies used wooden frames covered with thin sheets of steel. Continuous vibrations from the long driveshaft shook the entire structure so intensely that bolts loosened and wooden joints weakened after only a few months of regular service. Passengers often joked that riding one of these buses on rough roads felt less like transportation and more like sitting inside an enormous concrete mixer. The shaking became unbearable, and steep hills created an even greater threat. Under heavy load, the twisting stress on the long driveshaft sometimes exceeded its limits. When that happened, the shaft snapped with a terrifying metallic scream, instantly leaving the bus stranded. Engineers quickly realized the obvious conclusion. The long drive shaft had to disappear. Their first idea sounded simple enough. Instead of sending power all the way to the rear axle, why not drive the front wheels instead? Eliminating the long shaft would solve the vibration problem in one stroke. On paper, it looked brilliant. Reality had other plans.
The first icy hill exposed a fatal flaw that physics refused to forgive. As soon as a heavy bus began climbing a slippery incline, gravity shifted almost all of its weight toward the rear. The front wheels, now carrying far less load, lost the pressure needed to grip the road, while the rear wheels became even more firmly planted. Think of a playground seesaw. When a heavy adult sits on one end, the child on the opposite side is lifted effortlessly into the air. A front-wheel drive bus behaves much the same way. The heavy passenger compartment pushes downward on the rear, unloading the front axle. With almost no traction left, the drive wheels either spin helplessly or skim across wet grass, mud, snow, or ice. The tires scream, throwing up slush and dirt, yet the massive vehicle barely moves. Worse still, the driver begins losing steering control because the front wheels are no longer gripping the road well enough to guide the bus.
Even when engineers kept the drive wheels at the rear, leaving the engine in the front continued creating another dangerous imbalance. Whenever the bus carried only a handful of passengers, nearly all of the engine's enormous weight rested on the front axle, while the rear drive wheels barely pressed against the pavement. That imbalance turned something as ordinary as wet leaves, muddy pavement, or a thin layer of ice at a bus stop into a serious obstacle. The rear tires spun endlessly, grinding away rubber without moving the bus even a single inch. Drivers often had to rely on surprisingly creative tricks just to get their vehicles moving again.
Before World War II, drivers in the Ural region experienced this problem almost every winter. Soviet GAZ-08 buses regularly became trapped on icy hills because their rear axles simply didn't carry enough weight. The rear wheels, the very wheels responsible for moving the bus, couldn't generate enough traction to climb even modest slopes. The solution was as unusual as it was desperate. Drivers often had to stop halfway up a hill and ask every passenger to get off. But the passengers didn't simply stand on the roadside waiting. Historical records describe how they crowded onto the very back platform of the bus, or even stood on the rear steps. Together, they bounced with all their weight, rocking the vehicle in an effort to press the rear wheels harder against the slippery road. Sometimes that still wasn't enough.
This dangerous tendency of rear-engine buses became painfully obvious during testing of the first German Mercedes-Benz 03-21 city buses in the mid-1950s. On rain-soaked cobblestone streets across Europe, drivers discovered that the heavy rear end could suddenly lose grip if they entered a corner just a little too fast. Without warning, the back of the bus would swing violently outward. Some buses spun sideways across narrow streets, clipped roadside barriers, and sent pedestrians scrambling out of the way. Recovering from the skid demanded exceptional skill and lightning-fast reflexes. Even experienced drivers struggled, because once that massive rear section started moving, ordinary steering correction simply couldn't overcome the tremendous momentum. Engineers eventually reduced this pendulum effect through careful suspension tuning, softer springs, and revised wheel geometry. But while solving one problem, they accidentally created another.
By moving the engine more than 12 meters behind the driver's seat, they completely disconnected the driver from the machine. In a conventional truck or front-engine vehicle, the driver sits close enough to hear every change in engine speed. They can feel the vibrations through the chassis, recognize the exact moment the clutch engages, and shift gears almost instinctively. Years of driving build an almost physical connection between the driver and the vehicle.
To make it work, engineers stretched a complicated linkage beneath the floor that ran nearly the entire length of the bus. It consisted of long steel rods, universal joints, pivots, brackets, and connecting arms linked together over a distance exceeding 12 meters. Drivers nicknamed the mechanism the gear maze. It looked simple from the outside, but the system constantly fought against nature. During hot summers, the long steel rods expanded. During freezing winters, they contracted. Road vibration, dust, and constant movement gradually wore down every joint along the linkage. Before long, excessive play developed throughout the entire mechanism. Instead of making precise shifts, drivers found themselves moving the gear lever through enormous arcs, searching blindly for the correct gear. The sensation was often compared to stirring a giant pot of thick soup with an oversized spoon.
Because the engine sat so far away, drivers couldn't hear its RPM over road noise and rushing wind. They had to guess the right moment to shift. Too often, they guessed wrong. The transmission answered with a harsh metallic grind as gears collided instead of meshing smoothly. Over time, those grinding shifts chipped away at the gear teeth, scattering metal shavings throughout the gearbox and dramatically shortening its lifespan. A breakthrough finally arrived in the late 1960s with the legendary Soviet GAZ-06-30 bus. Instead of forcing drivers to wrestle with a 12-meter mechanical linkage, engineers introduced a revolutionary solution: an automatic hydraulo-mechanical transmission. Power was no longer transferred through a traditional clutch that depended entirely on the driver's timing. Instead, a hydraulic torque converter used transmission fluid to transfer rotational force smoothly from the engine to the gearbox. The principle was surprisingly elegant. Imagine placing two electric fans face to face. Turn one fan on, and the moving air causes the second fan to begin spinning without the blades ever touching each other. A torque converter works in much the same way, except it transfers energy through rapidly circulating fluid instead of air.
The result transformed bus driving. The transmission selected gears automatically, adjusted itself to road conditions, and eliminated the constant grinding caused by missed shifts. Drivers no longer had to rely on guesswork, and passengers enjoyed noticeably smoother acceleration with fewer jolts and interruptions. For the first time, the rear engine layout seemed close to perfection. But hidden inside the tightly enclosed engine compartment at the back, another problem was quietly growing. The engine was beginning to overheat. Unlike a front-mounted engine, which constantly receives cool air as the vehicle moves forward, the rear engine sat trapped inside a confined compartment with very little natural airflow. As speeds increased, the bus's large, flat body pushed air aside like a giant moving wall. Behind that wall, something unexpected happened.
A large, low-pressure wake formed at the rear of the vehicle. Instead of drawing in fresh, cool air, this turbulent zone pulled dust, dirt, exhaust gases, and road debris upward from behind the bus. Ironically, the cooling system was forced to breathe the hottest, dirtiest air available. The next engineering challenge had begun.
The overheating problem wasn't caused by the engine itself. It was caused by the way air moves around a bus. A modern bus has a tall, flat body that slices through the air like a giant brick. As it travels down the road, it forces huge amounts of air away from its front and sides. But behind the vehicle, something very different happens. Instead of smooth airflow, a large, low-pressure zone forms at the rear. Engineers call this the wake region. Rather than supplying cool, clean air to the engine compartment, this invisible vacuum acts like an enormous industrial vacuum cleaner. It constantly pulls in road dust, muddy water, tiny stones, and even the bus's own exhaust gases, swirling them into a turbulent cloud behind the vehicle. Unfortunately, that's exactly where the engine radiator sits. Unlike a front-mounted radiator, which enjoys a steady stream of fresh air while driving, the rear-mounted radiator is trapped inside this dirty, turbulent airflow. Instead of breathing cool air, the cooling fan is forced to suck in hot, contaminated air filled with dust and debris.
The consequences appear surprisingly fast. After only a few weeks of driving on dusty suburban roads, the radiator's delicate aluminum cooling fins begin clogging with a thick mixture of dirt, engine oil, and road grime. Layer by layer, the buildup forms an insulating blanket that prevents heat from escaping. Once that happens, the engine can no longer cool itself properly. Even a moderate uphill climb on a warm day becomes enough to send coolant temperatures soaring. Within minutes, the engine begins to boil over. Drivers of the famous Soviet GAZ-03-30 buses fought this problem constantly while crossing the mountainous roads of Crimea and the Caucasus during the summer. Long climbs combined with high temperatures often pushed the cooling system beyond its limits. Experienced drivers developed their own unofficial solution. Before tackling a steep mountain pass, they would partially open the rear engine hatch and secure it with wooden blocks or homemade metal hooks. The raised panel acted like a giant air scoop, catching fresh air from the sides of the moving bus and directing it straight into the engine compartment. It looked strange, even unsafe, but it worked. That simple trick often provided just enough additional airflow to keep the engine from overheating before reaching the summit. Eventually, engineers solved the problem properly. They designed sophisticated hydraulic cooling fans and ventilation systems capable of drawing cooler air from roof-level intakes instead of relying on the dusty airflow behind the bus. Engine temperatures became far more stable, and overheating gradually stopped being a routine concern. Just as one engineering battle ended, another began. City planners and transportation authorities introduced a completely new requirement. They wanted buses with floors so low that passengers could step directly inside from the sidewalk. Elderly people, wheelchair users, and parents pushing strollers all needed easier access.
It sounded like a simple request. In reality, it forced engineers to redesign the entire drivetrain. Traditional buses carried large, solid axles beneath the floor. Between the rear wheels sat a bulky differential housing that protruded upward into the passenger compartment. As long as that hardware remained in place, the floor could never be lowered enough. The solution demanded a completely new type of axle. Engineers developed what became known as the portal axle. Imagine a perfectly straight axle connecting two wheels. Now picture bending both ends upward into the shape of an upside-down letter U. Small reduction gears at each wheel allowed the axle beam itself to sit much lower than before, dramatically lowering the passenger floor while keeping the wheels at the correct height. It was an ingenious breakthrough. Passengers could now board almost directly from the curb without climbing multiple steps. But this innovation created another difficult question. Where could the engine go now? It could no longer lie flat beneath the floor because there simply wasn't enough space. Mounting it horizontally across the rear would block the aisle and eliminate valuable passenger room.
Engineers needed one final redesign. Instead of laying the diesel engine flat, they turned it upright and installed it vertically inside a tall, narrow compartment in the left rear corner of the bus. Mechanics quickly nicknamed this enclosed compartment the wardrobe because it resembled a standing cabinet. Power still had to reach the offset portal axle, so engineers designed an angled driveshaft that transmitted power through a carefully engineered set of gears, despite the unusual layout. By the early 1990s, manufacturers such as MAN perfected this concept. Their portal axle designs allowed buses to feature completely flat floors from front to back, giving passengers effortless access while hiding nearly all of the complex mechanical systems inside one compact rear corner. It was a remarkable engineering achievement. But placing one of the heaviest components of the bus so low and so close to the rear bumper introduced a new safety concern, one that wouldn't become obvious until the moment of a rear-end collision.
So, the next time you see a bus with its engine tucked away at the rear, remember that its position wasn't chosen by chance. It represents the outcome of nearly a century of engineering, where every design solved one problem only to reveal another. From violent vibrations and poor traction to toxic fumes, overheating, dangerous skids, and crash protection, each challenge pushed engineers toward a better solution.
Modern buses are the product of thousands of tests, countless failures, and decades of innovation. Their quiet cabins, low floors, smooth handling, and impressive safety standards exist because engineers refuse to settle for good enough. Behind every ordinary bus ride is an extraordinary story of physics, persistence, and problem solving. A reminder that even the simplest everyday machines often hide some of the world's most fascinating engineering.